NTU World of Wisdom. Welcome to High Impact Thesis. In this podcast, we speak with researchers from various scientific fields to talk about the motivation, goal, and potential impact of their research. We also want to give you a sense of how a Ph.D. is carried out with an emphasis on the PH, the philosophical aspects involved in pursuing a Ph.D. So welcome to the High Impact Thesis podcast. And today's guest is Mr. Rohit Behera. Rohit, thank you for joining us today for our podcast.
Thank you, Christopher. Thank you for having me. So let me introduce myself a bit. So I'm Rohit Pratyush Behera. So I'm officially in third year of my PhD. Just started recently. So it's been July. So yeah. So third year in my PhD. So I'm in mechanical and aerospace engineering. So just to introduce just a brief description of what exactly is like my work is related both to mechanical and material science. So I'm taking advantage of both the fields. Yeah, that's it.
So if you could tell us a little bit about the motivation behind your work at a higher level, not specifically your PhD work, but the larger scheme of things. What is your field trying to do? What is the motivation behind the kind of work that you are a part of?
Yeah. To explain this, I would just like to give you an example. You all must have been familiar with biological things, right? Just for example, the beehive, right? Like the beehive you have seen. Just to give you an example, you have seen the hive, right? You all must be familiar with the hive. So
Yeah.
it's basically inspired from the honeycomb structure.
Mhm.
Yeah. So why is this inspiration is important? Just want to say because first of all, the idea is to have low material consumption. Then second is to have high specific strength stiffnesses and as well as lightweight for this kind of structures, and as well as it has good insulation of sound properties. So basically you take in a nutshell. So this is what the inspiration has been taken from the nature. So just precisely talking about the motivation, nature has, like we believe as a material scientist as well as mechanical engineer, talking about my field, nature has the solution for everything. So if you see around, so if you see people, I mean, we have evolved. I mean, even all the biological animals have evolved. For example, just a small example, you see a snail, right? So it had a protective shell protecting it. So it has gradually developed like since a long period of time. So this is a motivation for my research. So what I mean to say is that nature has solution for everything. So if we see around and take inspiration from the nature and try to put all this kind of mechanisms and all those things into artificial materials, so we can do wonders. So that is all my motivation for my research.
Nice. So that's an interesting thought. And I hear of, not sure if it was Boeing or Airbus, that when they designed the aircraft, they were inspired somewhat by some bird. I don't know what bird, but I can definitely see why it might be worth looking into nature, because nature has been around far longer, right? So
Yep.
there's definitely a
Definitely.
lot to learn from there. Cool. And so let me just understand this. You said that you are in a mechanical engineering school, but dealing more with materials, it, or material science. Am
Yep.
I right?
Yes, you are
And
right.
so your research is you are collaborating with your material science, or did you have to learn the material science side of things? Since I suppose you're originally a mechanical engineer, or
Yep.
maybe tell us a little bit about your background
Yeah, definitely.
and how you got here.
Yeah. So previously, I did my master's from Indian Institute of Technology. It's from the Indian School of Mines, Dhanbad, Jharkhand, which is in India. So there I was working on this, traditional fiber composites. What I mean by traditional fiber composites is like the glass fibers or the carbon fibers. You must have seen carbon fibers in supercars, right? If you fancy them a lot. For
Yeah, I've
example, the
heard of them. Yeah.
Lamborghini, yeah. Everything is made of, long carbon fibers, and they're super lightweight. Okay. So now, when it comes to, like, for example, talking about this, since you picked up the topic of mechanical engineering and material science, so I believe that the mechanical things we study is based on a particular material. So if you have a strong background on material science, you understand your material. Since I'm not dealing with any particular material, right? So we need to understand the chemistry behind it, and from the chemistry, then we go to science, then we go to engineering. So I think everything is interrelated. So if
Mm.
you work on a very interdisciplinary kind of field, for example, which combines different kind of factors, for example, like in my case, the material science and the mechanical engineering, I think many aspects can be revealed and be understood well. So yeah,
Mm.
so this is the background behind me.
Nice.
All right. So now we want to zoom a bit more and take a look at your own research process and your research life as a postgraduate student. So, if you can give us some of the core objectives of your own research with more details, perhaps now, and let's focus more on the specifics of what you are doing, and also give us a sense of how your day-to-day research activities looks like and what kind of tools you use to carry out your research.
Yeah, definitely. So yeah, so since you to ask me about my research, so first thing I would like to say about the particular biological animal I'm taking inspiration from.
Mhm.
So I'm not sure, but you might have heard eaten the shrimp, right? For example, this kind of water animal called shrimp, which is
Yeah,
yeah, yeah, yeah. So
Yes.
there is another kind of species which is called the mantis shrimp.
the one with
Mantis.
colorful.
Yes, yes, exactly. Yeah,
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 yeah.
yeah, exactly. Yeah. So if you might have noticed, it has like a two kind of spaces are there. So one is called the spearer, one is called I think the hammer or something. I mean, yeah, I mean the striker or something like this. I forgot the exact specifics. So what I'm tracking one of it, the one which has a hammer kind of attacking like of structure. So
Mm.
it is called the dactyl club. So basically, people call it the biological hammer. So why
Mm.
is it called the biological hammer? Is that so I'm taking here two specific examples of underwater animals. So one is the abalone shell, so which
Mm.
is also very famous, and people take inspiration from it and try to build several kind of structures. And another one is abalone shell. Sorry, another one is the dactyl club of the mantis shrimp, or to be specific, I'm taking inspiration from the dactyl club. So what this mantis
So
shrimp
you
does,
take inspiration from the what?
mantis shrimp, the dactyl club of the mantis shrimp,
The Dactyl?
dactyl club.
The Dactyl Club. Okay.
Yep, yep, yep. So it's a kind of club. Yeah, how will I say? It's called the biological animal, to put it in simple words.
Okay.
Yeah,
Uh-huh.
yeah. So what this specific animal does is that it preys on this abalone shell, or the seashell. So it tries to impart repeated forces and try to break its structure, and then take home this specific this abalone shell for dinner. So just
Mm.
imagine how powerful it would be. Like it imparts repeated impact strikes, and it can go up to an acceleration of around 10,000 G with a force of 1,500 newtons, which is quite
Okay.
high for an
Wow.
underwater animal. Yeah, yeah, yeah.
Yeah.
Yeah, it's quite fancy, like people have been working about it. So yes, so how can the question now arises, how can it do it? So if
Mhm.
you dig in, like since people have worked on it, like several researchers have been done, so it's mainly because of the structural alignment within its dactyl club. So it has a very complicated kind of structure, and that is the beauty of nature which I'm talking about here.
Mm.
So so my work is based on taking inspiration from the microstructure of this biological hammer, or you can say the dactyl club.
Mm. Mm.
Okay,
I see.
yeah. So talking about now the specifics of how I do it. So what I do is like I have my this ceramics. These are kind of disc shaped ceramics. Okay. So now, in order to specify it in a particular structural orientation, they need to respond to certain kind of field. Okay,
Mhm.
you need to direct them, you need to make them respond to a certain kind of field. So for this, I'm trying to make my platelets, or the disc shaped ceramics, magnetically responsive, and I'm using magnetic field to direct it according to my directed orientation. So this is how can I arrange this you know specific disc shaped structure in a certain kind of arrangement.
So, so let me just clarify there. So
Yes,
you
yes,
said that you have you studied this mantis shrimp
yes,
thing,
yes, yes.
and you see that it applies lots of
No,
force.
this is the background. This is the motivation for my research.
Oh, okay.
Yeah, yeah, yeah. So I'm
Mhm.
trying to make some structure which is inspired from this biological hammer.
I see. I see.
Yeah, yeah, yeah.
And what you currently control is the magnetic field or the electric field. How do you apply the? Maybe just mention a little bit. Maybe I didn't understand like what you yourself do from
Yeah,
after
yeah.
moving from
Sure, 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 sure.
inspiration.
Okay, okay. So when you talk about this biological hammer, so it has a very
Mhm.
complicated microstructure.
Right.
To be specific, it has a kind of a kind of a herringbone kind of structure or a helicoidal kind of structure. So it means helicoidal means it has like a, you can relate to helical kind of structure. For example, like a spiral structure. Okay, so this kind of structures are very complicated to make. You cannot make it just by like some basic or general additive manufacturing techniques. You need to apply some kind of field to your any kind of material maybe to make it something similar. Okay, so what I do is I use ceramics, because the thing of ceramics is it's very hard. It has very lot of strength, and also this kind of ceramics have been found in this biological hammer. So what I'm trying to do is I'm trying to make the ceramic, which is very commercially available, magnetically responsive. Okay, by inducing some kind of magnetically responsive substances, and then trying to control the orientation to make it a helicoidal structure or a helical structure using magnetic field.
I see. I see.
Yeah. So it's basically like directing or making the entire structure with the help of magnetic field. Yeah, something like this. Yeah.
But I wonder how can a ceramic material be responsive to magnetic fields?
Yeah, that's a very good question. So now another thing comes into play. So we have this iron oxide. This which is also called magnetite. So this magnetite is very, very responsive to magnetic field. These are also called super paramagnetic iron oxide nanoparticles. So what I try to do is I try to absorb these nanoparticles on the surface of my ceramics. Okay, so this process takes an entire week, and when it is adsorbed on the surface of my ceramics, then my ceramic becomes magnetically responsive.
I see. So basically you blend the ceramic material with the magnetic responsive material.
Yep,
in this case, iron oxide, is it?
Yes. Yep. You got it right. Yeah.
I see.
Yeah.
So then the internal structure doesn't need to be. The magnetic field will only affect the surface. Am I right?
Yes. Now what we do is now you understood that magnetic field can control the microstructure, right? We can orient our platelets along different directions. So what if, imagine I have the whole system takes place in a colloidal assembly. So we have a colloidal system where the ceramics are dispersed in water or something like this. Then I apply a magnetic field to orient in a certain direction, right? So now the thing comes into play, like so it is a kind of bottom to top approach. So at first the system, like if you want to orient my particles, so you have to start with the bottom. Okay, so now you understand it's a colloidal system, right? So now the thing comes, how to make it a solid.
Yeah.
Right, because everything is a solid, you see. So what we do is at the bottom of the substance, the entire colloidal slurry, we have a gypsum mold. Gypsum is a very good absorber of water. Yeah, so I place, so I have this mold. Okay, so onto this mold I pour my slurry, which has this ceramic kind of thing. Then the entire system is assisted by magnetic field. I mean, with the help of different movement of magnetic field, you can control the orientation of the platelets, or I mean to say ceramics. Yeah, and when the entire process goes up, this water from this slurry or the colloidal system slowly drips out into the gypsum substrate. Yeah. So this is how the slurry is removed.
Okay.
I see. And then why would you use magnetic actuators rather than using normal mechanical actuators to move the structure in this case?
Okay, so now since my ceramics are magnetically responsive, so you need to apply, you need to, for example, disc shaped means you have a certain amount of surface area so that the platelets or the ceramics can respond, right?
Yeah.
So imagine, for example, if I keep my magnet at a certain angle theta, so my ceramics will be oriented or listen to that, this magnetic field and align themselves in a certain direction in which I place my magnetic field. Right. Imagine. Yeah. So this continues go on. For example, if I keep my magnetic field at a certain angle theta for a certain time, then my ceramics will be oriented at that certain, for the certain time, and then it will dry up. Then the top is wet now. Okay, so now when I try to orient the top system, then my ceramics, which are not dry, they're wet, they try to then again follow the direction of the magnetic field and orient themselves.
I
So
see.
it's
So
like a,
it's mainly for orientation purposes.
yes, it's like a bottom to top approach, where the bottom
Yes.
parts gets dried up first, then we go slowly to the top part. So yeah,
Right.
So
yeah.
if I bring in another strong magnet, will it destabilize or bring things? Will they be reoriented if I bring in a strong magnetic field, or
Yep,
once
definitely,
it's set in
definitely.
place, it's set in place?
Yes. That's a very interesting question. So, okay. So imagine, so now what happens is that I'm using another important thing is I'm using a very millitesla kind of field. For example, in my case, it's between 15 to 30 millitesla. So
Mhm.
imagine how responsive my ceramic is. And
Mhm.
for example, like you said, if we try to bring some strong magnet, it definitely will interfere it, and it will affect the orientation.
I see. I see.
Yeah.
So because I'm not sure how much of an impact the Earth's magnetic field has in this case,
Yeah.
whether.
So yeah, so only a few millitesla works quite well, and I have seen like beautiful structures. I mean, if you see like it's almost comparable with the natural system. All the natural system is a lot more complicated than the synthetic system, but yeah, I mean
Mhm.
it's very beautiful.
Nice. And are you able to observe these new structures, or you observe the behavior of the final? Can you look at them? How small are these structures or these arrangements? Do you look at it through a microphone, or do you just observe the properties and its behavior and then say that okay, it must have this structure internally?
Yeah, this is a very good question, actually. Yeah, so as to say, I'm trying to orient those micron-sized ceramics, right? So
Hmm.
it's very important to observe them, like like how they behave in certain micro scale. So for that, I use the scanning electron microscopy, where I can go to several nanometers or something like that.
Oh.
So yeah. So another thing, why this kind of orientation I'm doing is because if you see this biological system, like I said, it's very complicated. Like it
Hmm.
has very site specific properties, and if you test, for example, different regions, you will find different properties. So it's so as to say, to conclude, it's very heterogeneous, right? Like for example, it has very specific properties for a specific region, and it is because it is necessary for that specific structure.
Hmm.
So now,
Mhm.
why I am orienting is that there is some kind of anisotropy because of this orientation. Like for example, if you orient it in different direction, you will get different properties.
Hmm.
So yeah, so it's just like, for example, you use I mean, you can see carbon fibers, right? If you load them in the direction of alignment, or in the direction of the fibers, then it is strong. And if
Hmm.
if you load them opposite to the direction of the fibers, it's not that strong. So it's kind of similar. Yeah.
Hmm.
Yeah, so something like this.
Mhm.
All right.
So,
Thanks.
so
That's
in your
pretty detailed. Thanks.
in your case, like the end product for your work, like when you do the experiments and do different kinds of treatments and whatever, so the end product will be a ceramic uh, with metallic, maybe say nanoparticles, if that's correct, dispersed and oriented in a certain direction. That's
Yep.
how it looks like, right? At the end.
Yes. Yeah. Talking, since you talked about the application, let me elaborate a bit. So what exactly, like I explained you what I'm trying to do, right? Like I'm trying to toughen my ceramics, right? So these kind of structures I'm following to toughen my ceramics. That's the final goal. So if you ask about the applications, imagine what if, since the ceramic I'm using is super lightweight, it's very lightweight. You know that
Mhm.
in aircrafts we normally use aluminum, right? Like it's the most lightest metal you can get. Like normally mostly aluminum is used.
Mhm.
Yeah.
So imagine if we can follow such biological concepts, which is found to be very fruitful in the nature, and draw these concepts and put it in the artificial systems, following some complicacy, and then finally we are able to give some toughness. So imagine we can replace this aluminum in aircrafts, or even for energy dissipating purposes. For example, in automobiles, for example, the chassis, it's made of aluminum or something like this. So when you go for a crash test, so it needs to absorb the vibrations, right? So that's why you
Yeah.
use metals. Yeah. So imagine if this kind of structures are able to absorb these vibrations, you can use them there. And one another great example is the bulletproof armor. So you have seen, I mean, people normally use ceramics for the coating, right? Since it's very, like it's a perfect coating material, and it offers some wear resistance. I mean, if you rub it, it doesn't get weird easily, and it has
Mhm.
a good amount of strength and penetration resistance. So that's why they use as a coating metal. Why not make such kind of ceramics and use it as a whole, like a bulletproof armor, entire bulletproof armor made of ceramics. So it's a kind of very important thing. If we can do this, then of course, I mean, everything takes time. But if this concept can be applied to artificial systems with a proper blend of understanding the mechanisms and with a proper set of materials, then I think that this will be a great to try for commercial applications, maybe in a 10 to 20 years. I mean, everything takes time, like, yeah.
So as I'm going to ask, so as a researcher in general,
Yeah.
um, I wonder, you say that you're combining two fields, or at least working somewhat in two fields, and we would want our audience to know how you are able to navigate that. What are some more general tools that help you in your research? Maybe some, whether it is tips on how to read or whatever you have discovered in the process of doing the PhD, the tools that are specific to your work, but also that can be thought of as more general for our PhD students.
Yeah. Okay. So to start with, I would say it's very important to know about what we are doing. For example, when I came here, my like every supervisor, my supervisor also like handed me over a research proposal, and she, I mean, everyone expects to go through it entirely, like have a broad view, broad idea of what exactly you're doing. So yeah, I mean, first and foremost is to go through what people have done on and what exactly you want to use for your research. For example, there can be very like different fields to focus on. So I chose to focus on this particular direction to fabricate this and understand the mechanical properties, to be precise. So yeah, so first of all, it's very important to understand what people have been working on and what exactly you are trying to do, and your interest also matters. Like, as a general speaking, as a researcher, I mean, it's always good to understand your interest and then put it into work and derive some results and to understand what you're doing. And
Mhm.
third, more important thing is, yeah, I mean, it's not always necessary to work hard, but it's very important to interpret your results very nicely and relate everything. For example, if you're framing a story or trying to do something big, for example, projects are a part of several stories put together.
Yeah.
So yeah, it's very important to relate everything. Like, okay, from this you get this. Okay, how can be related to that? So it's
Mhm.
very important to put everything framed together and make it, compile everything and understand literally the meaning of what you get. So yeah, I think that's kind of very important as a part of being a researcher.
Right.
Sounds good. Okay. Um,
Uh,
so actually, at this point, or heat in the conversation, we tried to look at your field in a rather general sense, and then look ahead to next 10 years, next 20 years.
Okay.
So I like to think about it not as you and what you're doing, but like what you see happening, what are the likely breakthroughs, and so on.
Okay.
So I think I'd like to just learn a little bit about what are some things that have happened that are like the big things in your field, like the way that in biology you have like the discovery the DNA, or how cells replicate or whatever, right? Like those big things. And I'm wondering in your field, what are those moments?
Mm-hmm.
And then after that, we'd like just to talk a little about what are we seeing in the next 10, 15 years in terms of big applications.
Yep. Yeah. Okay. To start with, yeah. So actually, recently, very nice discoveries have been made, and very really good papers have been published on this. Especially when I talk about the mantis shrimps, since I talked about the biological hammer, right? So focusing on, so there are several parts of looking into it. So first of all, the main and important thing is it imparts impact resistance and impact resistant and damage tolerant behavior. So what I mean by those terms, when I talk about impact resistance, you remember I told you last time about the repeated impact forces, right?
mhm.
So imagine if at some point of time, since people have been working on it, so I saw some really complicated structures people have been doing, right? So imagine we are able to have this kind of structures, and by building this kind of structures, if you throw a very heavy ball at a really impact forces and continuously you keep on like placing hitting this structure with this ball, So it will have some cracks, but these cracks cannot pass through it, right?
Mm.
So I mean, just an example of similar kind of, you have heard about this toughened ceramic glasses, right? Which, for example, which is in this Apple phones. Recently, they advertised, and the girl who is, cannot hold a phone, and suddenly it drops over but it's not getting cracked. I mean,
That's
Mhm.
what toughened
I see.
toughened
toughened
ceramic.
ceramics, yeah, toughened ceramics,
I see.
yeah. So these are like, like we can build much better structures than what is available currently, if we are able to make this. Yeah, another term is the damage tolerant feature. So imagine, for example, if you are in a lift, you are in a breach, right? There can be cracks present, maybe due to anything. There are a lot of stresses, there are a lot of forces acting, there are a lot of movement. So a very important concept which can be derived from this, especially biological hammer, even from other biological structures, is this damage tolerant feature. So even if there is crack, this crack is not able to, flow through this kind of structures very easily. What do I mean by this is, although there is crack, the crack is not able to, like, fail the structure catastrophically. This is a very important thing which people have been working on, especially on ceramics, and they have been really successful in doing this.
Mm.
Yeah.
Uh, it seems to also have some wide range of applications in structural engineering or in like materials used for building any kind of structures.
Yep, definitely. Yeah, even you see this like this buildings made of concrete and everything. These are all like examples of ceramic composites, I would say. So this is similarly to my field. I'm working on the ceramic composites. So yeah.
Yeah.
I mean, you will find a lot of examples, like like a very inevitable form of examples, like where you have to use these structures and make it something so that it doesn't fail, very easily or catastrophically, so that so that it's durable, as well as, I mean, like it provides you strength, like for even for that longer period of time.
Mhm.
Yeah.
Is there a future where the material, once you have made this object made of your material, for example, then you reprogram that material so that it acquires new properties, like I guess the alignments, the way the things are aligned,
Yeah.
determines these properties in the physical world. And you mentioned just a moment ago that the magnetic field can still have an impact on the material after it's been made. Do you think in the future that might be a thing where you have a material and then you want to use it for a different purpose? I don't know, maybe improve its conductance or whatever. Then you bring this magnetic field close and reprogram it.
uh,
Does that
uh,
seem?
to be honest, like, so okay, so the one you heard was like during the preparation of my samples. So
Uh-huh.
after that, it undergoes a very firing process. So after
Ah,
that, it becomes a very hard and stiff kind of structure. So that after that, it doesn't respond to magnetic field.
I see. I see.
So
Oh,
Okay.
yeah.
okay.
So yeah, I
Okay.
mean, if you try to reprogram it, it will be only during the processing stage, not after the processing stage.
Oh, I
Yeah,
see.
So
I
yeah.
see. Okay.
yeah,
That's
But
a.
I think there are some materials in which this idea is applicable. The idea of modifying the properties of the material using electric field or magnetic field. For example, I think there are some certain kinds of smart glasses which can change the transmission by applying electric field.
Yep. I mean, you are talking about responding to external stimuli, right?
Yeah,
Yeah,
exactly.
yeah.
Yeah.
So okay, so one example of my lab I would like to give you. So people have prepared this, this morphing kind of structure. So it is inspired from the Venus flytrap. You know this plant,
Mhm.
right?
Yes,
Touch
Yeah,
me
yes.
not.
yeah,
It's very
The
famous.
one that closes once
Yes.
something lands
If
on
if
it,
if
right?
if you, if you touch it, it suddenly closes it, right?
Uh-huh.
yeah.
It tries to trap its prey. So in my lab, so they have made similar kind of. It's called the morphing stuff structures, which responds to high temperature. So if you
Mhm.
cross a temperature beyond a certain limit, it will just try to morph or kind of change its structure to a certain position. And then
Mhm.
if you go back to the temperature, it will just open up. So it's a very nice
Yeah.
responding to external stimuli. So imagine it being used as a robotic gripper. Yeah.
And it's a nice switch as well. I guess you could use it for switching things on and off.
Yes,
You can
switching things,
connect it up
carrying
and
loads. If it's strong enough, it can carry loads and etc. stuff. It's very
Yeah.
interesting. The programming thing is it's very interesting.
down.
Yeah.
I guess I'm interested in this because I think materials, I mean, I guess ultimately, uh, at the, I guess at the very low level, all matter is the same, right? Where it's a matter of arranging things in a particular way that it becomes a different, so to say, element. And so I guess there is a future where you just have this one object, then this object, once I want to use it for a different purpose, I sort of reprogram it. I mean, technically that's what we're doing, except the processes are much longer, right? Like you are using this material for this purpose. Some people use ceramic for another purpose, so it goes through different set of processes, but it's still sort of say the same matter. So I'm just thinking that in the future it might be possible perhaps to do it using new tools and maybe program it on the fly or maybe faster. That'd
Yeah,
be
yeah,
exciting.
definitely. Yeah, like the way you said, one factor is another, the scale factor, right?
Mhm.
You talk about tunability, and there is another factor which is coming to play. Imagine, what if we can, like have this kind of facility or kind of power, so that we can tune the structure from the nanoscale till the, I mean, and extend our structure till the or centimeter scale. Like we
Mhm.
have the control of tunability. So
Mhm.
that's another factor. So I am now able to control in the micron scale, but people
Mhm.
have been also working to control or build similar structures, trying to tune them from starting from the nanoscale. So if you
Mhm.
have this kind of power of tunability, you can try to orient your structure in any direction and achieve, for example, certain properties in certain direction and different properties in the other direction. So which is
Mhm.
kind of very, yeah, like the way you said, we can program structures.
Mhm.
Yeah, yeah, yeah.
Mhm.
Responding to magnetic field, electric field, depend on the which materials are using and how it is responsible to different fields.
I see. I see.
Mhm.
Yeah, yeah, yeah.
So you work primarily with ceramics at some, you say you have something at the bottom, then at the ceramics are involved in your work, or did I
Yep,
miss?
yep, 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 yep. Ceramics are my basic work, and I'm trying to make ceramic composites. So yeah, so
Okay.
it's a ceramic polymer composite. So finally, it will be used for this. Like I said, the applications will be like bulletproof armors, like something for shock absorption or provide some kind of toughness. Yeah.
Mhm.
The idea is
Mhm.
to, make it multifunctional so that it has strength, stiffness, toughness, as well as along with lightweight features. This
Mhm.
is the kind of
I see.
whole objective of my work.
And just a question on the uh, properties of it. Like, do you have control, or do you just measure at the end? Like things, I mean, materials usually we talk of, I guess, the Young's modulus and those kinds of properties.
Yep, 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 yep.
Do you plan for those, or you just do whatever and then you measure at the end and say, okay, the Young's modulus is this, or do you have control beforehand?
Yeah, that's another very interesting question. So when I talk about this tunability, so
Mhm.
that is where these factors come into play. Okay, so now this, we can orient our structures, my structures, right? My structures can be oriented in different directions. So when it comes to Young's modulus and properties about hardness and for example even toughness, to
Mhm.
some extent, so what happens is that they offer some kind of anisotropy. So what I
Mhm.
mean by anisotropy is they give different properties in different directions. So the idea of also doing this structure is you can put this kind of or make this purchase suitable where you want to apply load. For example, I need load in I need to apply load in a certain high load in a certain direction, whereas in the other direction I do not need to apply high load. So
Mhm.
this kind of structures can be used in for this particular applications also. For
Mhm.
example, like you talked about the Young's modulus, right? So the Young's modulus in certain direction would be higher, whereas in the other direction it won't be that higher, depending on the orientation of my ceramic particles.
Mhm.
Yeah.
I
Mhm.
So
see.
this is kind of the anisotropy which is comes into play in my research. Yeah.
Great.
Okay, all right. So let's now move on to your personal interests
Yeah.
outside your research field. So, what kind of things you find interesting or enjoy spending some time on in your free time? So, it could be some hobbies, activities, or any other topics that might be of interest to you. So, if you could share with us some of that.
Yeah, yeah, sure, sure, definitely. So one interesting story is that so when I was doing my masters back in India in the IIT IIT Dhanbad, Jharkhand. So I used to do modeling over there also. So modeling,
Mhm.
bodybuilding, and then some kind of cricket, sports has always been a part of my life. So
Yeah.
yeah, so so the bad thing is that after coming here joining PhD, so I'm not able to do modeling. But yeah, I mean all the bodybuilding still is into play. So yeah,
Uh-huh.
but again, PhD has certain demands which you have to fulfill. There's no way out from it. So
Mhm.
Yeah, that's
so
right.
yeah, the most of the time is consumed in doing research and understanding what exactly I'm doing and interpreting the results. So
Mm.
yeah, I mean, although I have interest in a lot of things, but I mean, at some point of time, we all have to sacrifice since we are on the same page. So
Yeah.
For sure,
PhD.
for
So
sure.
yeah,
Yeah.
so that's what I have more interest in. So mostly sports and this all extracurricular activities. Yeah.
Mhm.
I see your also. I mean, you and I at least have interacted through TEDx NTU. So I
Yeah.
guess you are a person interested in ideas in general, or maybe you could also just share about the I guess the philosophy of why you decided to do a PhD, live a good, I don't know if it's good or bad, like a good modeling career, potential modeling career, and then you choose a PhD. Was there any philosophical or deep reason for it, or was just like, let me just do a PhD?
Oh yes, this is another important, very interesting and important question. So like yeah, I mean, when you see modeling, it looks really good from the external world. Like whenever you are an audience, you really tend to acclaim and like praise. Oh my God, that guy is doing modeling. It's not exactly entirely the way you say it. To be
Okay.
precise, yeah. So there are several struggles, and to be exact, you don't get paid well. Whatever effort that you put. So yeah,
Yeah.
so that's one of the more important reasons. And then again, although I mean it sounds fancy, but the maintenance it asks, it costs you a lot, honestly. And again,
Mhm.
I had also interest in research, so
I
I
see.
had to choose a way like to pursue my career in this modeling, or go into research. So I
I
definitely
see.
chose research because I feel it's more support you, like monetarily as well as mentally.
Okay.
Mm.
Okay.
Yeah.
Well, I hope every now and then you can do modeling just for the fun of it, not for the, because now you're like, well, your money side is settled and so on, and then every now and then you can do a
Yeah,
bit of
definitely. And
modeling.
oh, yeah, old model is not a bad thing though.
Yeah.
Okay. I think we have really explored a few areas with you, and we are supposed to ask questions that probe you. But I suppose there might still be other things that you feel are important or relevant, or worth sharing about what you do. So we like to just let our guests just share whatever really about your field, maybe something that new people have never heard of, or people outside the field have never heard of, that's really exciting for you.
Yeah, definitely. Okay. So yeah, so in a broad sense, like as you know, as I told you, I'm working on, I'm taking inspiration from the nature and trying to, make structures or something, and similar to that of nature. And since nature has solutions to many of our problems,
Hmm.
because nature keeps on evolving.
Hmm.
Yeah. So for the general audience, I would say like it has a lot of scope, not just for mechanical thing, or it has like from electrical backgrounds, from like for example into neural networks and etc. Like a lot of things can be learned. But
Hmm.
again, it's very diverse, and you need to understand what exactly nature does. I mean, it's too complicated when you are studying a living being and taking inspiration from it. Even people those who have already done works on these living beings or in the nature, so it's too complicated. Just taking an example of a human bone, right?
Hmm.
It supposes a lot of load, and it supposes a lot of things. If you cut the structure and you see from different papers and different works which have been done, it's too complicated. It's not easy to replicate or mimic exactly those kind of structures. So the one thing is you can the nature, like it, I would say it's the perfect example of everything which it has done yet. Understanding is another important thing, and mimicking and taking inspiration is another whole different important thing. So I
Hmm.
mean, just I would suggest that I mean it's really good to explore nature and understand what exactly and how it evolved, and what are the properties it can offer, and why it is happening, reasoning everything. So yeah, I mean, it has plenty of opportunities, different areas, different fields, and yeah.
Yeah, for sure. Yeah, I mean, I think it provides a lot of insight for developing new technologies and
Yeah,
in a
yeah,
wide
yeah,
range of areas. Yeah.
Even people are talking about, for example, bioimplanting structures, right?
Mhm.
You have heard about human tooth and etc. The
Yeah.
What?
dentin, the human tooth. So
Oh,
yeah,
human.
my prof had in her PhD had made some human tooth. I mean, you can try to replicate similar structures and put it like as a replacement in your body as a human tooth. I mean, that was
Oh,
just a prototype. Yeah, yeah. So I
interesting.
mean, yeah, this kind of structures can be done. I mean, it's so interesting, and the materials used are really biocompatible. For example, people are using calcium phosphate for as just for instance, it's very biocompatible. So
Hmm.
I mean, using this kind of structures, I mean, you can go for dental implants. A lot of things can. It's so wide, it's so vast. I mean, understanding it like it's very complicated. It's I mean, when you, for example, since we are doing with simple things, right? When you talk about heterogeneous structures and try to study its properties, it's like a whole another level kind of study. So
Hmm.
yeah,
Yeah.
and like several parameters come into play. You cannot exactly sense that because of this parameter this effect is taking place. This is very difficult to take into
Hmm.
account and derive or conclude something from it.
Mhm.
Yeah,
Nice. Well, Rohit, thanks a lot. I love that you are passionate about what you're doing. This is showing through, and we want to wish you all the best for this PhD.
yeah, yeah.
This is very exciting
Yeah.
work, and so we appreciate that you have shared this with us. Thank you very
Thank you so
much.
much. Thank you
Yeah.
so
Thank
much
you
for
very
inviting.
much. Thank you very
Thank you,
much.
Christopher. Thank you, Mohammed. This
Thank
was a
you.
really lovely talk having you both. Yeah.
All the
All
best.
right.
Okay.
Thank
All
you.
Thank
right.
you. Thank
Bye
you.
for now.
Thank you. See you. Bye bye.
All right. Goodbye, everyone.
Goodbye.